So today, Kendra's going to be talking about effective and reproducible data visualizations with demos in Python. Um, Feel free to get started. Thank you.
Awesome. Thanks so much for the introduction. I'll just share my screen. All right. Can you see my screen?
Yes.
Okay, awesome. So today I'm going to be doing an intro to data visualization, focusing on reproducibility and how to make figures effective. And I'll be giving some demos in Python. So there'll be two main parts. First, I'll talk about visual decoding. So that's when you see a figure and then you understand what it means. And then I'll talk about visual encoding, which is when you have an idea for a figure and you create it using code. So first, visual decoding, also known as seeing a figure and understanding what it means. So first, let's talk about space. So understanding positions, areas, shapes, etc. And can participants, they can't speak, but can they say things in the chat?
Yeah, they can leave
Interaction.
comments in the chat, and they can use the Q&A function as well.
Okay, so either think to yourself or say in the chat, which do you think is 2 times the black box, 2 times the size of the black box, the green box or the pink box? And which great, I'm seeing some responses. And which of the circles, the red, the pink or the green, do you think is twice as high as the black circle? And same question for here. So this is supposed to illustrate that it's easier to decode information. So it's easier to understand values in a chart when you have positions on an aligned axis instead of, say, positions on an unaligned axis or areas. So the correct answer for all three is green. And I just illustrate that there. The pink is 2.5 times. So this relates to perceptual errors we make when visualizing amounts or values on a figure. So this figure from this great textbook by Tamara Munzer shows which types of figures we make more errors on. So we make the fewest errors on a bar chart where the bars are close together and they're aligned. We make more errors when there's stacked bar charts. Because that is like having unaligned axes for some of the areas in the stacked bar chart. And we'll talk more about that later. Pie charts, you may have heard that you shouldn't use pie charts. Well, the reason is that it's hard to decode information from pie charts. It's hard to guess how much this area is based on the angle and the area. Same for circles and squares and rectangular areas. So now let's talk about color and lightness. I'm going to ask a similar question. Which of the boxes do you think is 2 times as light as this box here? Do you think it's the middle box or the right-hand box? Okay, so it's actually the middle box. So sorry, my headphones just died. Can you still hear me?
Yes, we can.
Okay, awesome. So this is just to show, again, that it's hard to decode information based on lightness. And now we're going to talk about that with color, and I swear this is the last one. So if you look at all of these squares, they all have the same physical lightness, but you might have thought that the green box was lighter. And that's because humans have an uneven Oh, somebody raised their hand. Should I take questions now or at the end?
I think they unraised their hand.
Oh, they unraised their hand. Maybe it was a mistake. Okay. So the reason why the green seems physically lighter is because we have an uneven perception of lightness over the color spectrum. So we perceive green that's physically the same lightness as red as lighter. So here we see the perceptual lightness based on perceptual experiments. So essentially, this is showing that when you're making a data visualization, it's not a good idea to use this kind of color map because people are going to perceive contours and values differently. Even though they're the same physical lightness, they're different perceptual lightness. So what you should use is a psychophysically accurate palette, where if you want values to look different, say on a color map, the colors systematically change with the perceptual brightness instead of with the physical brightness. So has anyone heard anyone say that you shouldn't use the jet color map? The jet color map. Oops. Oh, sorry. Sorry, I'm having a problem with my slides. I'll just scroll through here. If anyone's used Jupyter Rise, it's a little bit touchy. That's what I'm using for this slideshow. So the jet color map is basically just a rainbow with all the colors being the same physical lightness. And you'll notice that it looks like there's a contour near the green because of the change in perceptual lightness at that stage. So that's why people say don't use the jet color map. So this all relates to physical versus perceived intensity of different channels of communicating information. So you can see that for length, which is what is used in, say, a bar chart or a scatter plot, as you change one unit of physical intensity, you change one unit of perceived intensity. So that's why it's easy to decode information in a bar plot or a scatter plot. And that could be why they're popular. And whereas something like brightness, if you change, say, 2 units in brightness, you need to change more of the physical intensity in order to get the same perceived intensity. So you have to change 5 units of physical intensity to get 2 units of perceived intensity. So I find this really fascinating, and this is relevant because choosing color maps can help you communicate information, or it can confuse people. It can communicate information that's not actually there. So it can be misleading. So that's why it's important to use color maps that are designed to be perceptually uniform. So here's just a cheat sheet showing for different kinds of data what kind of color map you could use. So if you have continuous data that's sequential, meaning like there's a natural bottom of the data, like 0 and a natural upper level, you can use a sequential color map like this. Whereas if you have diverging data, say you have negative values and positive values in, for example, a correlation, you can use a diverging color map so that say this area here in the negative matches this area here in the positive, so that the magnitude of values can be decoded effectively. And then if you have discrete color maps, there's discrete versions of all these color maps. And for categorical data, you want to use a sequential color map that has been discretized, because this means that every element in every different color also has a different brightness. And this means when you put it in grayscale or consider people who have color deficiencies, like colorblind people, you can still decode the information because every color also has a different lightness. So I've put this here. I'll share the slides at the end, and this is another cheat sheet. I won't go through the whole thing, but it will help you decide what kind of color map you need for different kinds of data. And this brings me to redundant encoding. So when we talk about matching color and brightness, that's a kind of redundant encoding, but there's also other ways you can encode information redundantly. So for example, in this chart, which we've already seen, they encode the different lines in different colors, but they also label each line right beside the line. And I think this is really effective because if they had a legend, you'd have to remember the color and go to the legend and figure out what it is. So these are little things you can do to just make it slightly easier for people to understand your figures and to decode your information more accurately. So now we're going to have a bit of discussion. So get ready to type in the chat. What do you think works or doesn't work about this graph? So this is a very old graph. I'll zoom out a little bit. From the 1700s, showing the imports and exports of England. And I think it's actually a very effective graph. And I'm curious what you think makes it effective, kind of based on what we've learned so far. The labeling of phases. Do you mean like the balance against and balance for? I think that's what they mean. There's like a natural distinction between this area and this area, where before there was a balance against England, and then in 1750 something, the balance became in favor of England. And just having these areas shaded differently and labeled makes it really easy to interpret the message of the graph. So they didn't have to add these. If they had just had the line of imports and the line of exports, people could have figured it out. But this way it jumps out at you, what is the message? The other thing is it uses values on a common scale. So it might seem obvious that you should use this, but you can think of these charts like line charts that are really common and realize the reason why they're effective is because they use points on a common scale. So that makes it easy to decode. So now we'll talk about another very early example of data visualization from the 1800s. This was by Florence Nightingale, who was trying to show the causes of death or mortality. The causes of mortality in the army. And I'll ask the same question. What do you think works about this figure? Can you understand it? Can you not understand it? Maybe put in the chat what you think works or doesn't work. Okay, radio silence. I'll give some ideas. Oh, hard to decode, specifically when the black slices are side by side. Yeah, a large amount of text to describe the colors isn't helpful. Yeah, this instead of using a legend, which maybe hadn't been invented yet, maybe no one had thought of using a legend yet at this time, they describe the areas of the blue, red, and black, what they mean in text, which is actually kind of hard to read. And I agree, it's hard to decode what are the values of, say, the black areas, because for one, it's hard to decode angles, so it's hard to get the values from this type of visualization. And also because these bars or areas of the circle are stacked, it's hard to compare like this area to this area, or say this one to this one, and actually decode what the numbers are. Yeah, it wasn't clear to me immediately that they were on the same scale. Yeah, exactly. Thanks for contributing in the text, in the chat. So there's this really great website called Storytelling with Data, and they have these challenges where they take popular data visualizations like these two, and they ask people to recreate them and try to improve on them. So this is one of the entries where they tried to improve on Florence Nightingale's chart. And do you think it's an improvement? What do you think maybe is better or worse? While you're thinking, I'll just point out a few things that stand out to me. Well, they have text here that, again, like this chart here, it immediately tells you what the main takeaway is from the chart. I'm just going to read the chat here. It wasn't clear to immediately that there were, oh, that was, I like that the info is all in the same place rather than split between two graphs. So it's simple, more simple to understand. Yeah, that's true. On the one hand, it's easier to understand the one graph, but actually on the other hand, it's a bit confusing that there's more than 1 year in a circle. I find it a bit confusing because I kind of visualize a year as being a circle in itself. The other nice thing is they label some of the numbers. So even though it's hard still in this format to visually decode what the information is, you have the information labeled. So that's an example of effective redundant encoding. I like how they tell the time order. Yeah, exactly. So having it all in one circle is perhaps more effective because it's easy to see which bars come after other bars. However, I would argue that this data visualization of the same data is actually the most effective. It immediately shows you that there's 3 categories and makes it easier to compare them because they're all using the same scale, and you can compare them more directly. So as we said before, it's not the easiest to determine values from color or lightness, but they've used a perceptually uniform scale here where the color is changing systematically with the lightness, just using just one color here. So I think this is a really effective way to show it, and it highlights this important time where they had improved action plans to improve sanitary conditions. So I don't know if that was obvious in the last graph, but it becomes obvious in this one that there is a difference between this year and this year, this time and this time when they didn't have good sanitary conditions and when they did have good sanitary conditions. All right, so the next thing I'll talk about is contextual adjustments that you need to make. So it's important to consider how people can decode your information, but you also have to consider where they're going to see the information. So in academia, typically people see charts in presentations or in posters or in papers. And as you move left to right, you need more time to understand the figures. So that's why, say in the paper, you can have a really complicated figure with multiple subplots and text to explain it because people can take as long as they want to understand it. Whereas for a slide, you have to consider how long it'll take to decode this figure and how long they'll actually see the slide. So if those two values mismatch, you should simplify your figure. So also in the in papers and posters, there'll be more proximity, so they'll be closer to the visualization. You can have more text, explanations. It should be more self-explanatory in a paper because you're not going to be standing there explaining it to people, and you can have more visual complexity. So the most important takeaway from this section is that there's different channels that you can use to display quantitative information, orders or categories, and some of them are more effective than others. So this shows in order which are more and less effective. So again, position on a common scale is very effective, very easy to decode. Positions on unaligned scales is harder. And as we go down, volume is really difficult to decode. So don't do those 3D bar charts that are so easy to make in Excel. And then for categories, spatial regions are easy to decode, and color hue, it gets more difficult if you start using different shapes. And I added here text, not to the bottom because it's the least effective, but just because that's where I had room to add it. It can be really effective to label things right in the figure instead of having a legend like we saw before, because it just reduces the cognitive load that little bit and helps people understand your figure. So are there any questions at this point? And once we answer some questions, I'll go into the next lecture, which has more code in Python. I'll just give you a moment to think if you've got any questions. No, well, feel free to put them in the chat or raise your hand, and I'll answer them as we go along. Oops. Okay, so part 2, visual encoding basics. So this is when you have an idea for a figure and you write code to create the figure. That's what encoding means in this situation. So first, why use code to generate figures? Well, it helps you to make future adjustments because you just have to change your code and rerun it and it'll recreate the figure. It helps others reproduce your figure and they can adapt their figure for your figure for their own research. So it helps with the sort of collaborative side of science. And it also lets others build on your code. And it's more efficient in science if people are coding their figures and analyses and sharing them so that people don't have to figure out how to redo them every time. It's just more efficient if we're sharing. So what makes a figure reproducible? Well, first of all, the data is shared in a fair way, and FAIR stands for findable, accessible, interoperable, and reusable. So that means people can find your data, it's accessible so they can understand it, it's interoperable, which means it can be used with different software, so it's not like a certain format in a proprietary software. And it's reusable, so it's easy to reuse and build upon. And then the second feature of what makes a figure reproducible is that the code is open and usable. So that brings me to, what if I can't share my data? First of all, well, you can still share the code and you can simulate similar data in order to show how the figure is rebuilt. And I'll be giving some examples of simulating data to sort of redo figures. How can I make my code reusable? Well, this is a big topic, but basically you need to make it readable. So have lots of comments and use variable names that are understandable. Share the requirements, so which packages are required in order to run your code, and provide instructions and explanations. So first, let's talk about some common libraries in Python and some basic plotting. Actually, can I quickly ask in the chat how experienced people are with Python? Maybe say like beginner, medium, or expert? Very experienced. So far it looks like people are pretty experienced with Python medium. Okay. So I won't explain sort of basically how Python works. I'll just go into the data visualization part. So these are some common libraries. Matplotlib is perhaps the most basic library. Seaborn makes prettier graphs and it has more different plot types and can also do statistics for you. Pandas is, it can do plotting, but that's just one thing it does. It's really effective for dealing with tabular data and has plotting capabilities in addition. Plotly is for interactive visualizations, and I won't be using that a lot today. I just wanted to let you know that it exists. And I'll also be using NumPy for simulating data. It's not for visualization. It's for like doing math kind of stuff in Python. So first, let's make a bar chart with this data. Actually, here, I'll just run this so that if we want to change any code, the previous sections have been run. So let's make a bar chart with this data. First, X, the X variable. So on the X axis will be 3 different groups, A, B, and C. And then the values for each group are 1, 3, and 2. So in Matplotlib, it's very simple. You just do PLT, which is the short form that we use to load Matplotlib, to import Matplotlib, and then .bar, specify the X variable, specify the heights, and then you get a bar chart. Seaborn, again, is prettier. It does more plot types, does statistics, and it works really well with data frames, which we'll talk about later. So again, people are experienced with Python. I won't go into detail about this, but just know you can create a similar figure using Seaborn. You can put the data into a data frame. So this is like it's like a table where you can index data based on the rows and the columns. And you can use the data frame to also make a plot. And then Plotly, when you run it, it's interactive. So you can have different interactive components. This is very basic. It's just like if you hover over it, you see the value. So now let's put them into one subplot, into one plot using subplots. And there's some slight similarities and differences in how you input the data. Again, this is very basic. I just wanted to cover the basics in case anyone's very new, and we'll get into more complicated plots. And here there's an error on purpose. This line here got an unexpected keyword argument x. So most of these can take the argument x in order to specify which axis to put it on. But Plotly doesn't work well with the other libraries. You can't just insert it into axis that you created with Matplotlib. So Plotly is special. So now we've got the basics down. Let's make some more complicated plots while learning some data visualization do's and don'ts. So this is based off this great repository called Friends Don't Let Friends. It's Friends Don't Let Friends Make Bad Graphs. And it goes through a bunch of different examples and has code in R. So I here recreated the graphs using Python as both examples and as lessons to learn in data visualization. So first, Friends Don't Let Friends make bar plots for mean separation. And can anyone in the chat say why this bar plot is not an effective way to show mean separation? So you have 2 groups, you have a mean value for each group. And why is it not an effective way of describing the data? Standard deviation is high, not a normal distribution. Yeah. So the bar chart hides the fact that these 2 groups are actually very different. It looks like their standard deviations, well, their standard deviations are overlapping. you do a t-test and the p-value is very high, so you'd think you could conclude that these two groups are the same if you just did a bar chart and a t-test. But if you use a graph where you can see more of the distribution, you'll notice that the two groups are actually very different in the shape of their distribution. So here you have in group 1 values ranging from -2 up to say 3. But in group 2, you have all positive values and they go all the way up to 6. So even though the means were similar, the distributions are quite different. And this is most obvious here in a swarm plot, where you can see all the data points. So we're going to recreate this graph. This is the original graph from the Friends Don't Let Friends repository. So here I recreated the data, and I won't go into details of that because people seem pretty experienced in Python. I'll just show that once you have the data in a data frame, it's really easy to use Seaborn to create all 3 of these graphs. So don't think like this more sophisticated plot is more complicated to make. It's actually just as easy as the bar plot. These are just, these lines of code are just setting like the figure visual attributes. Like I got rid of the lines here and here using this line so that the figure just looks less busy. And I set the Y label and the X label. And then this line, tight layout, is really handy way of making figures just fit together well and not overlap in, say, the labels and the different parts of the chart. So here I've recreated them with just these 3 different lines for each plot. The basic plot just takes 1 line of code. And I want to think about this a little more. So the bar plot starts at 0 on the y-axis, but there are negative numbers, so that's another reason why it's not effective. And I also want to think about how we can redundantly encode information. And what if we still want to see the mean and statistical spread? How could we improve this swarm plot graph here? And my solution was to color the dots by with a diverging color map, like we talked about before, because there's a logical center of the data at 0, so it makes sense to use a diverging color map. And this highlights that one group has negative values and the other group doesn't. And then I show the median and the standard deviation so that you can still see the measures of central tendency. So you might think this is effective enough, but maybe this is a little bit more effective if you want to emphasize, for example, the negative values or that the medians are different. Yeah, any questions at this point about how I created this or how I've done anything previously? Feel free to put questions in the chat. I'd love to have these lectures be interactive. So next graph is Friends Don't Let Friends make heat maps without checking for outliers. And I come from neuroscience, from neuroimaging. It's really common to have heat maps of, say, correlations from neuroimaging. So you might have a correlation between each brain region and like pairwise correlations, and then you have a heat map showing all the correlations and you can see different patterns in it. But the problem is if you have outliers, it disguises those patterns. So here you'd think the pattern is, oh, these two stand out and everything else is basically the same. But if you max out the color around the 95th percentile, so instead of having the range go to 12, cut it off at 2, then you see this pattern in the data that you couldn't see before. So let's recreate this. Here I simulate the data, and now I visualize it. And as we go through these examples, the code is going to get more and more complicated, so feel free to like ask what different parts of the code mean. So this is a heat map. So here I create the heat map using Seaborn, and I make the maximum value of the color bar, the maximum value of the data. And then I create a scatter plot next to it here, showing all the values and their rank, and then coloring them with the same color map. And then to do this job better, I create the heat map, but I set the max value to 3 instead. And I do the color map with the same colors, and you can see the pattern. So, oh, somebody raised their hand.
Yes, there's a question in the chat.
Oh, there is. Are we going to receive the code after the talk? Yeah, I'll share. Actually, I can put it in the chat right now. It's openly available in this GitHub repository. It also has the requirements in it if you want to run the code yourself. So yeah, creating this kind of scatter plot is a really effective way to visualize how well your color map is doing in terms of outliers and actually describing the patterns in the data. So next, friends don't let friends make pie charts. This is maybe something you've heard before. Here they're saying, the pie chart, it makes it hard to compare groups. The arc length is redundant with the area. Here they're saying that donut charts are maybe a bit more effective. You're not relying so much on the angle, but it's a little bit like a stacked bar chart, just put into a circle. And here they're saying that having a stacked bar chart is the easiest way to compare the groups. So I would argue, yes, this is more effective than a pie chart, but actually I think there's a more effective way, because stacked bar charts essentially make you decode values with unaligned axes, like in this example we saw before. So if you want to understand how different the orange one is from between the groups, it's very difficult because you have to calculate, okay, this goes from 50 to what, 80? So that's 30, and then you have to calculate this one in order to see the difference. Whereas when they're aligned, like at the bottom here, it's a lot easier to decode the information. So I would argue that actually splitting these all into mini bar charts is a more effective way of comparing groups. So let's first let's make the data. I make a data frame for each of the groups. And here I'm showing how to make this fancy layout for your subplots. So it might be a little confusing, but once I recommend you draw it out and then specify where each of the subplots will be and then code it. So here for the top left one, I'm adding a subplot where there's two rows and 4 columns, and it's the first one in that setup. And for the next one here, again, 2 rows, 4 columns, and it's the second one. Whereas for this one, say at the bottom right, I'm saying there are 4 rows, 4 columns, and this is the 16th one. So does that, if that doesn't make sense, let me know and I can explain it in more detail. But it takes a little while to figure this out, but it's more effective to do it this way than to say copy all your graphs into something like Inkscape or Word and then try to arrange them next to each other, because if you have to change one little thing on your figure, then you have to rearrange them all again. And believe me, I've done that before, and it's not a very efficient way of working if you have a lot of iterations in your figures. So here I did the same thing here. And in the first plot, I create pie charts, the second one, the donut charts, and the stacked bar plot. And then I do a stack of individual bar plots. And again, I argue these are a little more effective for actually decoding the values because the axes are aligned for all of the different types. So finally, my last one is friends don't let friends make word clouds. This is something I added. I do a lot of text analysis, and amongst people who visualize text regularly, word clouds are a little bit of a pet peeve, and hopefully you'll understand why after this. So the data for this is based on a survey I did where I asked the question, if you do open science, what kind of resources did you find most useful for learning how to do open science? And these are the kind of answers I got. I specifically took out connecting words and stuff, or stop words. If you know a little bit about natural language processing, I kind of pre-processed this text so it was really simple so we could see exactly how the word cloud was created. So here, for example, you see hackathon 3 times, and school 2 times. So let's look at the word cloud and see how that's encoded. So you can see that hackathon is bigger than school, but also hackathon is just a longer word than school. So it's not clear how the length of the word factors into the size. And there are a lot of other channels that are being used that don't actually mean anything. So they're using colors, but this color is the same or very similar to this color. Lecture and hackathon are very similar colors, but they're different sizes. So it's clear that color doesn't relate to size, but we don't know if color actually means anything. I think it's just prettier. And also, what does it mean when words are sideways? It's not clear either. So we can ask ourselves, how much bigger is hackathon than school? Well, we know it's 1 value, but that's really hard to decode. How does word length factor into size? What does color mean and lightness mean? And why are the words placed where they are? Putting certain words beside others could lead to different associations that might be unintentional. So we can make a more interpretable graph by just using a bar chart with the count on one axis and the words on the other axis. And it's not as pretty. Maybe you could argue that this one helps certain words stand out immediately, but this one is a lot easier to decode the information accurately. So now I've gone through all the examples, and we'll just briefly peek behind the scenes. So if you've ever looked up help, like say on Stack Overflow for bar charts, or for figures, not just for bar charts, you might have noticed that there's different ways of doing the same thing. So these 2 sets of code do the same thing. They make the same graph, but they're different styles of coding. So this one is explicit. So you make the axis object here, and then you're using methods on that object in order to create the plot. Whereas here you're calling the library pyplot again and again. And I think people generally recommend the explicit one because it's more object-oriented and more sort of Python-ish, but you can do things either way usually. It's also a little easier, I think, to control what you're doing if you use the explicit way of programming, because you know exactly where you're putting it. Like if you use, like you know exactly that you're putting the plot on this axis, you're putting this plot on this axis. Whereas here, if you say created a new axis in the middle, it would just go on the latest axis you created. So you really have to keep track of your code. So if your code gets complicated, you should use the explicit object-oriented method. There are 3 different layers of matplotlib, which again is the most basic plotting library. So at the back end, we have the figure canvas, which is the area into which the figure is drawn. What you might think of as the pen is called the renderer. It's an object that knows how to draw on the figure canvas. And then finally, the artist is the object that knows how to use a renderer to paint on the canvas. So most of the time, 95% of the time, I'd argue, you would be working with artists. And there's 2 types of artists. One type is primitives, which are things you can draw, and the other is containers, which is where to draw them. So for example, the figure is a container and the line you draw here is a primitive. It's a simple object that you draw onto the figure or onto the axis. And this anatomy of a figure chart is very handy for remembering the syntax for doing different common goals for editing a chart. So you might remember here, oh, to make the figure initially, I do plot.figure. To create a line, I do x.plot. To make a scatter plot, it's x.scatter, and so on. So what actually is an artist? Well, there's this very not super helpful explanation on the Matplotlib website where it says it's an abstract base class for objects that render onto a figure canvas. Typically, all elements in a figure are subclasses of artists. So it's hard to know exactly what it is, probably unless you're a programmer who works on Matplotlib, but essentially know that usually you're working with artists and there's things to draw and places where to draw them. And those are the essential things you need to know behind the scenes in Matplotlib. And that's it for this lecture. I think there was a raised hand. What's the difference between figure canvas and figure artist? So figure canvas is the back end where the figure is drawn. So it's a good question. I honestly, because I haven't looked into the code, the the code behind Matplotlib, I just use Matplotlib. I don't understand all the differences. Does anyone in the audience know the difference, perhaps? Some people said they were very experienced in Python. So I just think of the canvas as like a literal canvas, and then the artist as the thing that knows how to draw on the canvas. I don't know if that helps at all. Okay. Sorry, I don't have a better answer. But are there any other questions? I can open up to questions now. That was it for my lecture. Sorry if I'm a little short on time. I was hoping for more interaction, but it's a little hard when there's only the chat. Oh, you're welcome. I love talking about data visualization. So. Does anyone come up with any particular problems in data visualization that they'd like to ask about? Do you use ChatGPT for making plots at all? I've heard it's good, but I don't use it that often. I was using GitHub Copilot for a little while. My free license expired, so I don't use it anymore. That's basically in VS Code where I typically do my programming. It will suggest next lines for you. Oh, sorry, doesn't have code in it. So if I was typing here, I might say like X equals, and then it would like suggest how to finish the line. And that was kind of handy. It was annoying when it wasn't guessing what I actually wanted to do. And then I had to like ignore what they were suggesting while trying to think of how to do what I wanted to do. So I have mixed feelings about it. As for actually going to like the ChatGPT website and doing it, I haven't done it for Python because I'm pretty familiar with Python. I have done it when I've been working on websites, which I'm not as familiar with JavaScript and HTML. So I've like gone there for a starting place. The thing about using large language models for coding is you do have to know what you're doing to some extent because it will do things that don't make sense and you have to catch it. It might be more effective to ask questions on something like Stack Overflow and you have a person who will answer you and give you a particular answer. Sorry, there's one last question from Mansoor. Oh, maybe that was the last question, the one from Nadia.
I have a question.
Oh,
Nobody
yeah,
has
go
one.
ahead.
So what did you use to make the slides? It was really cool.
Oh, yeah. So they're made in Jupyter notebooks. I use an extension called Rise. I think it's just like pip install Jupyter Rise to install it. And if you do that, you can render. Oh, this is already open. We'll override it. You can open a slideshow right from the Jupyter Notebook thing, and it's handy because you can have code right in your slideshow. But the time when it's not good is if your code ends up creating something that doesn't fit on the window, like here. Or like as I get into the more complicated plots, like there's just so much code that you can't see everything. And here it's working pretty well. But like the nice thing is I could go in here and do the different things and you can see the output. Sorry, I pressed the wrong thing.
So that's Jupyter Rise, RISE.
Yeah, RISE. Yeah.
Yeah. Thank you.
Anymore for reusability, is it better to build plots in functions? Is it always the case that plots are implemented in functions, or is there cases for OOP implementations? So if you're recreating a plot many times, it's handy to build a function. If you're just making it once, it might actually be, your code might actually be more readable if you just code it like in a script. There are different opinions on it. I've looked up this question before. Some people suggest you do like everything in a function, but then when you're actually running the code to build the figure, people always have to refer back to the function to see what the function's doing. And that actually can make it harder to read. And I don't think it necessarily makes the code more efficient, again, unless you're doing the same plot over and over. So here I did pretty much everything just as scripted. Just in scripting, I didn't use functions very often. I don't think I use them at all. Oh, you're welcome. Thanks for coming. What is Open Science Hub? That's a good question. Open Science Hub. You mean Sci-Hub, or do you mean Open Science Office Hours? That's the thing that they mentioned in my introduction that I helped to organize. Yeah, sure. Okay, here, I'll go to the Open Science Office Hours website. So Open Science Office Hours is a group of people who are trying to help researchers make their work more open. And we do that in 3 ways. We have monthly lectures on open science topics, and we do weekly office hours. And to attend the lectures and to go to the office hours, you can be anywhere in the world. And the third thing we do is we have some open science resources. So this is the last lecture that we had earlier in June. If you scroll down here, you can see past lectures. So in the fall, we started with a theme of open data, and we had like intro to open data, intro to the brain imaging data standard. So it's kind of focused around neuroscience, but a lot of the things are helpful for people not working in neuroscience. Like I did a lecture on intro to Git and GitHub. We have recordings for all of these, and we're in the process of uploading them, but some of the first ones already have their recordings online. So you can just go on the website and click on it, and it takes you to YouTube where we have our recordings. So yeah, that's if you just Google Open Science Office Hours, you'll find it. If you go on Twitter, oh, that's not Twitter. were, I think, Oso McGill. And we announce all of our events on Twitter. Sorry, I'll just find the handle. It's, yeah, Oso_McGill. And we're not having lectures for the rest of the summer, but in the fall, we'll be starting a series of lectures on open publishing. All right, well, thank you all for your participation. The labeling of faith. Oh, there's more questions. Okay, thank you very much. Very useful stuff. Good. Yeah, I'm glad it was useful. Thanks for participating in the comments, and I hope you learned something. I guess there's a poll that you can fill out. Oh, that's great. Now I'll receive some feedback.